was asked to introduce a speaker who probably needs no introduction, Yuval Perez, who will talk about Cutoff on Ramanujan graphs. John spoke with Eyal Lubetsky, which has nothing to do with Lubotsky.
But as you see, the talk has something to do with Lubotsky. Well, the title hints. So, thank you. It's a great honor to speak in front of this distinguished audience. Ken. Oh.
Yes.
So. Okay. Right. Well, I know I speak on behalf of all the other organizers and many people here about what a special experience it was to learn mathematics here in the Hebrew University from Hillel, Benji, and others here. The topic I'm discussing has a lot of connections to Jerusalem, which I'll mention later. This is Cutoff on Ramanujan graphs, joined with Eyal Lubetsky, who is now at NYU. So first, a few words of background, okay, which there are many experts here. So we will be talking about regular graphs, D regular. All the vertices will have the same degree D, and focus on a special class of expanders. So when we talk of expander, we really need to talk of an infinite family of graphs. So we have a sequence of graphs Gn, maybe not for all n, but for n going to sequence going to infinity. We think of Gn having n vertices, and look at the adjacency matrix of Gn. Sometimes we will normalize it, but usually we'll just look at the adjacency matrix itself. So n by n matrix with one for indicating adjacent vertices and zero otherwise. And we look at this n by n matrix and look at its second eigenvalue. So the first eigenvalue is the Perron eigenvalue. It's D, corresponding to the vector of all ones, eigenvector of all ones. That's the leading eigenvector. So we go to the next one after D, that's lambda 2. And for expander, we want that the lambda 2 of the graphs will be bounded away from D. D will always be at least 3. So Pinsker was probably the first to find that most graphs, according to a measure he used, just take a small number of permutations, say 3 random permutations, and take the union of the edges indicated by those permutations. Then with high probability, this is an expander. And there is further work by many others indicating that most deregular graphs are expander. In particular, there's a well-known work of Broder and Shamir to that effect. It turned out, however, as later in the story, that the best rigorous results were obtained with explicit constructions. The first explicit construction of an expander based on the Kashdan property T was done by Margulis. And moving on to measure the quality of expanders, there is some wall, some lower bound, which is the Alon-Bopana theorem, which in a sharper form was published by Neely, which is, again, Noga Alon in 91, which says that for any deregular graph on n vertices, lambda 2 is at least 2 root d minus 1 minus a small error that goes to 0 as n tends to infinity. So this is a constant over the diameter of the graph. And since the diameter is at least log n, we have this with some constant that depends on d that won't matter. And okay, one thing to keep in mind, this is the spectral radius of the adjacency matrix of the infinite tree. If you think of that as an operator on L2 and look at the spectral radius, you'll get 2 root d minus 1. And this is comes into the story. The notion of Ramanujan graph, defined by Lubotsky, Philip, Sarnak in '88, is can be thought of as corresponding to this bound. So and with this definition, we don't even have to think of a sequence. We can think of a specific deregular graph. It is Ramanujan if every eigenvalue, except for plus minus d, so we're allowing d and minus d, but all other eigenvalues have to be concentrated in a much smaller interval, namely their absolute value has to be bounded by 2 root d minus 1. And so, as I mentioned, Lubotsky, Felix, Sarnak made this definition and gave a construction, and similar construction was given independently by Margulis. And this was only for certain d, when d minus 1 is prime, and and this was extended, I guess, here by Morgenstern, if d minus 1 is a prime power. Only quite recently it's been shown that Ramanujan graphs exist for all degrees. So these were bipartite Ramanujan graphs. This is a recent work of Marcus Spielmann and Srivastava. I should mention this one is not constructive and, well, only partially probabilistic. So this is based on interlacing families of polynomials, and it's related, in fact, it's a simpler version of their proof of the Cadison-Singer conjecture, and it's a strange thing. It's not constructive, so they can't give you a specific graph, but it's not really probabilistic in the sense that they can't give a probability measure where with high probability it will produce a Ramanujan graph. It is, they use a kind of probabilistic argument on the characteristic polynomial that gives a positive lower bound for the probability of a graph being Ramanujan, and this bound is exponentially small. So they show the
bipartite graph in all.
So they work in a certain subclass of bipartite graphs, but even there they cannot show, they cannot give a probability measure which will produce for you Ramanujan graphs with high probability. They have a kind of inductive probabilistic argument which gives a lower bound for the probability, and this lower bound is exponentially small. So it's not something you will simulate and find, but it is a positive lower bound. So in particular, it gives you existence. So this is a summary, and not all results about what we know on some of what we know on existence of these graphs. That won't be my focus, but rather, given the definition of these graphs, some properties that follow. So just to visualize, this is the LPS, one of the LPS graphs. It's really a small piece of it. It has 12,000 vertices, and around every vertex it looks locally like a tree up to some small distance. But from the perspective of, and of course this is a Cayley graph, so it looks the same from every vertex. But if I look from the perspective of this vertex, locally it has a tree structure, but of course this has to break down somewhere, and the structure near the diameter is quite complicated, and that's what we are trying to understand. This is another view of a piece of the same graph. These graphs are involved. Maybe the simplest non-trivial Ramanujan graph is the classical Peterson graph on 10 vertices. You can write down the characteristic polynomial of the adjacency matrix and see there is the This is a 3 regular graph. There is the leading eigenvalue of 3, and the other ones are, minus 2 and 1. So they are in particular all less than 2 root 2, which would be, the corresponding threshold for Ramanujan. So this one is Ramanujan with room to spare. We'll say we will use that for illustration purposes later. Okay, so let me go back to the slides. Now, part of what we'll see is how the Ramanujan property really constrains the spectrum of the graph. And so I told you the Alon-Bopana theorem tells you that you cannot, the eigenvalues, so this, by the way, is a picture of the eigenvalues normalized to the interval from plus minus 2 root d minus 1. So we divide by 2 root d minus 1 and put the eigenvalues on the interval minus 1, 1. So there are the huge eigenvalues d and minus d that are not pictured here. But you see, after this rescaling, Alon-Bopana tells you that if the graph is large, then you cannot be constrained to a smaller interval. So you have to have eigenvalues reaching essentially all the way to the edge. And there is a related estimate by Serre that says if you look at any small interval here, say look at an interval of like 2 root d minus 1 minus epsilon, from that to 2 root d minus 1, in any interval of fixed size here, as n grows, a constant proportion of the eigenvalues will fall in that interval. So Alon-Bopana tells you, there are some eigenvalues in any interval here, and then a subsequent estimate of Serre tells you, well, you actually have, for any epsilon, a positive fraction of the eigenvalues must fall in such an interval. Now, what do you see in this picture is trying to depict on one graph two spectral measures. One is for this LPS expander with 12,000 vertices. So this is the graph you see in the foreground, and this graph is a Cayley graph. It's which suggests and indeed leads to high multiplicity of eigenvalues. So you see in the histogram these eigenvalues have very high multiplicity. What you see in the background is also a Jerusalem-related construction. So this is a random lift of the Peterson graph. So recall the Peterson graph in the previous picture. That's a nice Ramanujan graph. Now, one thing which seems to lead to Ramanujan graphs, but there is no proof, is start with any small Ramanujan graph that you know and take a random lift. What is a random lift? Every vertex in, say, the Peterson graph is replicated 1,000 times. Okay? So we have 1,000 copies. Now, if V and W are vertices in the Peterson graph, then now there are 1,000 VIs and 1,000 WIs. And what you do is you just pick a random matching of the VIs and the WIs. So this will, and you do this for every pair of neighbors in the Peterson graph. You look at the 1,000 copies of them and you put a random matching in. So after you do that, every vertex in the new, so the new graph will be of size 10,000 while the Peterson graph was 10. And every vertex will still have the same degree as in the original graph, because it has one edge for every edge of the original graph. This is the random lift construction, which has been investigated a lot by Nati Lineal and his collaborators. And it's believed that if you start from any Ramanujan graph, you do a random lift with positive probability, not with probability going to 1, but with positive probability that doesn't go to 0, you will get a Ramanujan graph. But this is open. We do know it's weakly Ramanujan. I'll come back to that.
Positive and not high probability?
Positive and not high. This is what simulations and some heuristics indicate, but okay. Now, in this case, however, this is just 10,000 vertices, so my co-author is a very adept with these calculations, and he checked that if you, he took the Peterson graph, picked a random lift, and he got a 10,000 by 10,000 matrix, and he diagonalized it, and after a couple of tries, he got one which is Ramanujan. So what you see here is a spectral measure for a particular random lift. of the Peterson graph, which, and this one is definitely Ramanujan. What?
How many tries do you have to do before?
Just 3 tries, so about 1/3 of them. But it's, but the point is, I mean, he didn't. If you do many tries, it's a positive proportion, which is, you know, hovers around 1/2 between. It depends on what, you know, exactly on some details. But it's, I don't remember the number, but it's not a tiny fraction. It's a substantial fraction. Seem to be Ramanujan. Of course, we don't have any rigorous estimate as n tends to infinity. But with n, which is 10,000, one can diagonalize the metrics and check. But the point of what... yes, but Eyal did it after he was already at NYU. Anyway, actually, he was visiting us at Microsoft, so this is fine. But one thing I want to mention, the point of showing this picture is to show that even though Ramanujan graphs seem very constrained, you still have a large variety of spectral behaviors possible inside this interval. It's still a rich collection of graphs. They're not all the same at all. Okay, so now I switch gears to the kind of other focus, which is random walks on graphs. And of course, our point will be to connect these two. So we're going to look at random walks on graphs and how fast they converge to the stationary distribution. And this can be measured in various ways, in particular in various LP spaces. But what's considered the gold standard, the way we measure distance, is the total variation distance, which is really half the L1 distance between two measures. And it can also be represented as the maximum over all sets A of mu of A minus nu of A. So here mu and nu are probability measures on the graph. For us, one will just be a uniform measure, and the other will be the distribution of the walk after some number t of steps. So in general, if we have a Markov chain with stationary distribution pi, in our case, pi will always just be uniform, but I still use the notation pi. So if you have stationary distribution pi, we measure distance to stationarity at time t by maximizing over the starting state x. This is the measure, ptx dot represents the probability measure of the distribution of the walk after t steps. So we look at this measure, compare it to pi, stationary distribution, and measure the distance, maximized over the starting vertex. If we are working on a Cayley graph or a transitive graph, the starting vertex doesn't matter, so you can ignore this max. In general, this is how we measure distance. And then the mixing time depends on the parameter epsilon. T mix of epsilon is what is the first time so that the distance goes below epsilon. This distance is easy to see. It's monotone decreasing in time. So once it's below epsilon, it will stay there. And so this is T mix of epsilon. And this is a topic of interest for many reasons for computer scientists, in statistical physics, in combinatorics. I even wrote a textbook about mixing times, but with 2 co-authors. Anyway, this is the mixing time. And a key definition we will use is the definition of notion of cutoff. So the question is, how much does the mixing time depend on the target epsilon? If I want to get within 1/10 of the stationary distribution, how long do I have to run? And now if I want to get to within 1/1000, do I have to run much more or not? So when I write here T mix of epsilon, I'm thinking of a sequence of chains. And so we have a sequence of chains, and T mix of epsilon depends also on which chain we are looking in the sequence. And we say that there is cutoff if T mix of epsilon hardly depends on epsilon. So if we look at the ratio T mix of epsilon and T mix of epsilon prime, and we go along the sequence of chains, then the ratio tends to 1. This happens in some chains and not in others. I'll give you some examples in the next slide. So maybe the simplest example, there are various examples without cutoff. Let me get maybe the chalk. So one simple example. So we always want our walks to be irreducible and aperiodic. So take lazy random walk on a cycle. From every vertex you go with probability half, you stay in place. Probability quarter, you move to each of the neighbors. So lazy walk on the cycle. The mixing time is n squared, but it's order n squared, and there's no cutoff. If you want T mix of epsilon, will be of order n squared log 1 over epsilon. So if you want epsilon, which is if you want epsilon, which is a quarter, you have to run a certain time. If you run to epsilon, which is 1 over a billion, you'll have to run much longer. So this is an example without cutoff. Maybe another example, even simpler to understand, is suppose your graph looks like this. It's two complete graphs connected by an edge. This is another example with no cutoff. And the reason is that mixing here is really corresponds to the event of crossing from one side to the other. I start on one side, and the total variation distance from stationarity is the very roughly, it's quite close to the probability I still haven't crossed this edge. And this has an exponential behavior. So if I look at the distance to stationarity, it will behave here. It will have a decay of this form. The other case of cutoff, the distance to stationarity, has a very sharp decay at a specific time, and somehow all the action happens in a small interval around some number. And the first example of cutoff was by Daikonis and Shashahani, and they used a very natural random walk on the symmetric group. See, where is the eraser hiding? Maybe it's behind the screen. Don't see it. Anyway, I can. So what they see. So what? There's one. Which table? Let's see one. No. מאחורי הלוח, okay. Yeah, sorry, didn't prepare the eraser. Yeah, thank you. So, you have, you can think of n cards, and the random transposition chain, you choose two cards at random. It might be the same card, and you swap them. Okay, so with probability 1 over n, you will choose the same card. In general, you choose two cards at random, you swap them. What is the mixing time here? Well, it's easy to see it's at least half n log n because of coupon collector. A random permutation just has one fixed point on average. So really, in order to, if you start from the identity, in order to mix, you have to destroy almost all the fixed points. And so it means you have to touch almost all the cards. And this is going to take you half n log n because you touch two cards every round. So that's the easy lower bound. And using basic facts on representation theory of the symmetric group, they showed that this is in fact sharp. So half n log n is the mixing time. And so there is a cutoff profile. A simpler example done slightly later by David Aldous is lazy random walk on the hypercube. So a point in the hypercube we can represent by a sequence of bits. Okay, so this is a sequence of n bits represents a point in the hypercube. And what is the lazy random walk? We choose a coordinate at random, and we refresh it. That is, we replace it by a fresh random bit. That's why it's lazy walk, not simple random walk. So how many steps like that do we need to mix? Well, obviously n log n is enough, because after n log n, the coupon collector tells us we've reached all coordinates. But in fact, in this case, you don't need to touch all coordinates. You're not working in the permutation group. And half n log n is enough, because if there are root n untouched coordinates, you cannot tell this apart from the uniform distribution. this is related to the fact if you take a binomial distribution and shift it by less than root n, this you cannot distinguish this distribution. In total variation, it's still very close to the binomial. Anyway, these are the classical examples of cutoff. An important point is that these in almost all the examples, there were a number of them, but they were all on graphs with growing degree. As the size of the graph grows, the degree also grew. It's true in the hypercube, it's true in this, and it's true in all the examples that were investigated until the last few years. And there is a reason for that. As we'll see, let me just give a hint ahead that in many of these proofs, analytic methods were used. If you want to use an analytic method, it's much easier to control L2 distance than L1. So L1 is the gold standard. That's really the measure of mixing. But L2 is what's much more accessible. So typically, to bound, people bounded the L1 distance from below by a probabilistic argument, and then the L2 from above by an analytic argument, spectral or representation theory, and then notice that they got the same upper and lower bounds. So this is true in all these examples, and hence they got cutoff. This approach, as I'll indicate, is doomed in bounded degree graphs because the L2 mixing happens really later than the L1 mixing. So you have to use something else. Okay, so I'll come back to this point about cutoff, but let's go back to deregular graphs. So Redmond in 2008 proved the conjecture of Noga-Alon that almost every random deregular graph, so by almost every, this is not probability 1, but probability going to 1, is weakly Ramanujan, meaning that lambda 2 is, so we let n tend to infinity, and lambda 2 will be close to 2 root d minus 1. So of course, in this estimate, the lower bound comes from Alon-Bopana, but the upper bound is what needed to be proved. This proof was about 100 pages. There is now a relatively short proof by Charles Bordenave of this fact. Again, here in this setting, it's conjectured that a constant fraction of these graphs are in fact Ramanujan. So a fraction going to to a limit which is strictly between 0 and 1, but this is not known. Now, another thing one can ask, how does the random walk behave on these graphs? Does it have cutoff? I told you one cannot do this by analytic techniques directly. Spectral techniques directly won't work, but Lubetsky and Sly used the probabilistic technique based on the construction. So random walk on a random regular graph, so you can, in fact, construct the random graph as you go. So you don't need to look at the whole graph when you start walking. As you walk, you construct the pieces of the graph that you need, and that turned out to allow them to prove that these graphs have cutoff. Now, these graphs are expanders, so the conclusion is most deregular graphs are expanders. That was well known, and have cutoff. That was the new result. However, in a closely related paper, they constructed examples of expanders that did not have cutoff. So just being an expander is not enough for cutoff. One conjecture I made back in 2004 is that for all transitive graphs that are expanders, we have cutoff. So we have an expander family, which is transitive. Then it should have cutoff. That's a conjecture that's still open, but at least one embarrassment has been removed. When I made that conjecture, we didn't know any example of a transitive expander sequence with cutoff. No counterexample, but no positive example either. Now we do know at least some positive examples, some sequence of transitive expanders, namely the LPS graphs that have cutoff. What? Highly asymmetric. So the graph that they constructed is very far from transitive. Okay, and so here is one theorem on any sequence of deregular Ramanujan graphs. Let's look at non-bipartite, because for bipartite you need to do something to deal with the periodicity. So let's look at the non-bipartite graphs. We know many of them exist. On any chess sequence, simple random walk exhibits cutoff in total variation, and the cutoff time is the smallest it could be, namely d over d minus 2 times log d minus 1n. Now, where does this number come from? If you have look at the deregular tree. Every deregular graph is covered by a deregular tree. If you look at the deregular tree, we can understand very easily how random walk behaves there. So if you have a tree, the random walk moves away from the root with probability d minus 1 over d, and moves towards the root with probability 1 over d. So the drift is d minus 2 over d. So the speed of the random walk moving away from the root will be d minus 2 over d. Now, if we want a chance to reach n vertices, we had better have a chance to reach a ball of radius log d minus 1n, because this tree, right, every vertex except the root has d minus 1 children, one parent and d minus 1 children. So you need to be able to, the distribution has to really have its support contain a ball of radius log d minus 1n, but because of this drift, the time it takes to reach such a support is d over d minus 2 times this radius. So this is really the minimum you need on the tree to be able to have a substantial chance to reach n vertices. And if it's true on the tree, it's true on any deregular graph, because they're all covered by the tree. So before this time, there is no chance to mix in any deregular graph. And what we say is Ramanujan graphs really achieve this absolute minimum mixing time. And the mixing time, no matter what epsilon is, this difference as n tends to infinity is going to be of order root log n. So this is something we conjectured for a long time, but the obstacle was, as I mentioned, that Ramanujan graphs, it's spectral data, and if you want to use spectral data, the natural thing to do is calculate in L2, and it turns out L2 doesn't give you the right answer. The mixing time in L2 is strictly larger. It's a strictly larger constant times log n. So you have to use something different. The diameter is indeed, okay, this is a very good question. So if you take a random deregular graph, the diameter is log d minus 1n. And for every deregular graph, the diameter is certainly at least log d minus 1n. But not all Ramanujan graphs have such a small diameter. So the bounds that we know are between log d minus 1n and twice log d minus 1n. And there are some examples that need strictly more than log d minus 1n to cover all vertices. But as we'll see, log d minus 1n is the right guess in a different sense to cover most vertices. So here is a graph calculated empirically from of the distance of simple random walk from equilibrium. On the left, so we take this LPS graph with 12,000 vertices and calculate the L1 and L2 distances, and we see that the L1 goes down well before the L2 goes down. And this is also captured in the asymptotic. So this is, we now know for any Ramanujan graph the profile of how the distance decays in L1 and in L2. In both of them there is cutoff at some multiples of log n. Rho is here 2 root d minus 1 over d. It's the normalized spectral radius of the tree. Anyway, the point is that these are different constant multiples of log n, and so the L2 distance goes down strictly later than the L1 distance. Okay, now key to the analysis is not to work spectrally with the simple random walk, but instead with the non-backtracking walk, which I'll recall the definition shortly. But for that, it turns out that the L1 and L2 decay happen at the same time. And that will allow to prove the theorem. So this is a graph of the L1 and L2 distances for the non-backtracking walk. And I'll connect to this graph later. So shortly. So as I already hinted, the key to the proof is to look at the non-backtracking walk. Before going to that, I want to indicate another corollary, not of the theorem, but really of the proof, which is a purely geometric corollary, not about random walk, something about the structure of these LPS graphs. This, and more generally, the structure of any Ramanujan graph. This is true even in the bipartite case. For every deregular Ramanujan graph, fix a base vertex x, most vertices y are in distance log d minus 1n, in the sense that the number that are further away than log d minus 1n, and here we take some log, the number is little o of n. So there can be vertices that are further away, but they're a negligible fraction. For any base vertex, most vertices are close by. Log d minus 1n, which is, if you were to go shorter than that, then it's trivially you would only capture a small fraction of the vertices. So the first time you have a chance to capture most vertices, in fact, you do. And since for some of these graphs, like the LPS graphs, they are known to have high girth, we can also get corollaries about existence of long cycles long simple cycles in these graphs. There are further geometric corollaries. Due to time, I won't get into these. Okay, I want to mention that many of the facts extend to weakly Ramanujan graphs. So these are graphs where the spectrum is bounded by, instead of 2 root d minus 1, we allow an error that tends to 0. So this recovers. We do know that the random deregular graphs and random lifts of Ramanujan graphs satisfy this. And the same conclusions hold for these graphs, except that the size of the window of root log n we no longer have. But the basic conclusions about the distance to first order, they still hold on these weakly Ramanujan graphs. And we can even allow a small fraction of the eigenvalues to be much larger. So if the graph is an expander and you have less than a power of n vertices, eigenvalues that are outside the Ramanujan interval, they could be arbitrarily far up as long as it's an expander, then the conclusions still hold. Another thing I'll just briefly mention is that we can, by the same techniques, analyze the LP distance for any p. And the LP distances have very interesting behavior. And the formulas, so this paper is on the archive, and there are, if you want to read the long formulas, we have exact formulas for the distance in LP for any p. It's an interesting function of p. I won't write down the function, but I'll just say that you can calculate for deregular graphs what's the fastest possible mixing time in LP. It depends on p, and it strictly grows in p. And we know that for all p, the Ramanujan graphs exactly match the lower bound. Let's get to this is a graph of, in these LPS graphs, how the LP distances go down for different p's. So we can calculate it exactly in the example and also in the asymptotics. Okay, so in the final part, I want to discuss the method of proof, which, as I said, is based on non-backtracking walk. Yes?
So this is for P constantly cut.
So this is a, okay, so here it's not asymptotic. This is the specific graph actually with 12,000 vertices. An exact calculation of the LP distances for different p. So here you don't yet fully see the cutoff because it's only 12,000 vertices. You start to see a hint. I mean, the decay is pretty rapid, but it's not, you don't yet see the cutoff. This is the L1 distance, so it goes down first. And this is different LPs. The dots here represent the L2 distance.
If we fix P, then for every P the cut of
No, it starts at different places. So depending on P, it's strictly monotone in P. No, no, it doesn't go to infinity. In fact, the LP mixing time is exactly twice the L2 mixing time. The L infinity mixing time is exactly twice the L2 mixing time.
And this is the limit.
Yes. So this is L infinity. This is the profile in L infinity. But this can be, there is a general relation that distance, because it's a self-adjoint operator, the distance in L infinity mixing time is exactly twice the L2 mixing time. This is that's completely general, yeah.
And what is dispersion of distance?
What?
Dispersion.
This.
So you have xy randomly all graph, and what's distribution? For example, what is dispersion? You have expectation log n, but
so
previous.
So this is not okay. So we're not graphing a random variable here, right? We're looking at the distance in total variation as a function of time.
Yes.
So the distance goes down very sharply, but there's no random variable. So you could.
No, I mean previous slide when you consider maybe once more. Yes, here. So this is.
Yeah. I see what you mean. Right. So here. Good. So the dispersion is actually order 1. And this is in fact very easy. It's true for any expander. Mm-hmm. So it just follows from concentration of measure that the dispersion is order 1. So the non-trivial thing is that where is it concentrated? But the dispersion just follows from, in expanders you have concentration of measure for the distance. This is what? It cannot be.
It's not always the diameter. It can be.
Okay, so. What?
No.
It cannot be 3/4 of the diameter. The what?
Typical distance.
Typical distance.
Log n.
Log base d minus 1 of n. Yes. Okay. It cannot be 3/4 of that, because 3/4 of that you have a tiny number of vertices. Of the diameter, right. Yes, okay. Yes, that's right. That's the diameter seems to be 4/3 times this, although the upper bound for the diameter is not proved. So the only rigorous upper bound, as far as I know, is twice log d minus 1n. Okay. So the final few slides I want to mention. So the tool is non-backtracking walk. The key is that for non-backtracking walk, you can analyze, L1, we can analyze the L2. That's the workhorse, which you can do spectrally. And then it turns out that for non-backtracking, the L2 and the L1 exactly match. And so we get the L1, and we get a good estimate for the L1. And then there is a simple relation between mixing for the simple random walk and for the non-backtracking walk. And that simple relation you most easily see using the covering tree. So what is the covering tree of a graph? You can think of it as the tree of non-backtracking paths in the graph. Fix an anchor vertex that we start, and look at all non-backtracking paths from that vertex. They have a natural tree structure, which is exactly the covering tree. So in order to implement a random walk on a graph, one strategy would be just run a random walk on the covering tree and project it down, because every vertex in the tree corresponds to some path and hence a point, a vertex in the graph. When you do that, it's the relation between simple random walk and non-backtracking walk becomes clear. Running a simple random walk on the tree, we know it will reach some random level, but about d minus 2 over d multiplied by t if we run for t steps. And that means that the distribution of the simple random walk will be a mixture of distributions of the non-backtracking walk, but the mixture at the time which is about d minus 2 over d multiplied by t. So once we understand the mixing of the non-backtracking walk, we just have to multiply this mixing time by this factor d over d minus 2 and get the mixing time of the simple random walk. And that works in, for total variation mixing. So it reduces the problem to analyzing the non-backtracking, the mixing of the non-backtracking walk. Now, what is the non-backtracking walk formally? It's a walk on the space of edges, right? We're not allowed to cross back on the edge that we just came. So the state space instead of vertices, it becomes directed edges. And from a directed edge, we can go to any of the directed edges that continue, except originally the edges were not directed, but we just add the direction. So we can continue on any of the edges emanating from that edge, but we're not allowed to cross back on the edge we just crossed. This means the degree is now d minus 1. Following every edge, we have d minus 1 choices. So so we have a matrix. The transition matrix here is indexed by edges. So u, v, and x, y will have an edge if v must equal x, and u has to be different from y. So every row in this, so this is a much bigger matrix. It's little n times d is its size by little n times d. And the sum on every row is d minus 1. So there is a formula known as the Bass formula that relates the eigenvalues of this matrix to the eigenvalues of the original matrix. Namely, if lambda is an eigenvalue of the adjacency matrix, then you solve this quadratic equation. You get two choices for theta, and both are eigenvalues for the non-backtracking matrix. So this has been known and used for some time. We enhance this by giving a full Jordan decomposition of the non-backtracking matrix. So this matrix, it's not symmetric, it's even not a normal matrix, so you cannot diagonalize it, but it turns out the Jordan form is very simple. It just consists of 2 by 2 blocks. So from the Bass formula, if all the eigenvalues of the original matrix A were all distinct, then it's natural to get from that these Jordan cells would just be 2 by 2. But the problem is, in the examples of interest, like the LPS graphs, the matrix A has high multiplicity on individual eigenvalues, and then it's not obvious that when you go to the non-backtracking matrix, you don't get big blocks in the Jordan form. And if you had such blocks, this would cause problems. But it turns out it's still always just 2 by 2. And moreover, you can calculate, I told you what are these eigenvalues, the thetas, but you can calculate also the off-diagonal term exactly. So in the Ramanujan case, all the off-diagonal terms have absolute value exactly d minus 2. So there is no mystery left on the Jordan structure of this matrix. And one can also say what happens for other eigenvalue. Just this term is completely determined by the eigenvalue in general. And that allows an exact calculation with the non-backtracking matrix. So here's a picture indicating the pairs. So the eigenvalues of the non-backtracking matrix come in conjugate pairs. For the Ramanujan case, they're all on the, they're not all the interesting ones are in this circle of radius root d minus 1. Here they occur with high multiplicity in the LPS graph. On the right, this is this random lift where the multiplicity is much smaller. Now going back to this picture, so this is the highest eigenvalue, d minus 1, the obvious one. Here we have some nuisance eigenvalues of size 1. They won't matter much. And the interesting eigenvalues are here. In the Ramanujan case, they're all of size root d minus 1. So note the the eigenvalues of A of the adjacency matrix are smaller than 2 root d minus 1, but what it transforms with this quadratic equation is all points. This quadratic equation is really a transformation that maps this segment on the real axis to the circle. So they're all on the circle of radius root d minus 1. This is, this has been observed for a long time. And finally, because we know the off-diagonal terms, they don't matter much. So here is just because of time, I'm going to just sketch the calculation that you do if you ignore the off-diagonal terms. So then you can just, this is the distribution at time t of the non-backtracking walk started at a directed edge xy. And if you want to calculate the norm in L2, then certainly in the transitive case and also in the more general case, you can calculate that explicitly using that Jordan form. And again, this approximately equal is because here I'm ignoring the off-diagonal terms and just writing the contribution of the diagonal terms. So these are the nuisance terms, these plus minus. So there are a lot of them, but they still matter little at this time. So it turns out you can ignore them. And these are the important terms. Each one is of size root d minus 1. So when you take it to the power 2t, this will be d minus 1 to the t. Now, this normalization comes from when we go from the non-backtracking adjacency matrix B to the probabilistic version, we have to scale by d minus 1. So this is the d minus 1 to the power 2t when you calculate the L2 norm. And then when we take into account how many of these there are twice n minus 1. And here we have d minus 1 to the t. So if we just take t to be slightly larger than log d minus 1n, then we get that this will be small. Now in reality, there are these off-diagonal terms, and they do cause a small perturbation, and that's why we lose an extra log to take care of these. This is related to the fact that if you take a 2 by 2 matrix, and let me take the simplest one, this, and you take it to a power t, what you get is not exactly given by the eigenvalues, right? You get 1t 0, 1. So this kind of linear growth is very mild, and it is easily controlled here by just pushing in the time in extra log. However, if you had larger Jordan forms, this wouldn't, larger blocks in the Jordan form, this wouldn't work. So in this slide, but I don't have time, it's just what it shows is there is an elementary verification of, this is well known, that if f is an eigenfunction of the original adjacency matrix, then how do you get eigenfunctions for the non-backtracking walk? Very simply, just by taking linear combinations of eigenfunctions of the original f. So if we have an edge xy, define a new function t theta f of xy, which is this linear combination of fy and fx with parameter theta. And initially, you don't know what theta is, but you take the matrix B, multiply by this matrix, and do a little calculation, and you get an expression like this, explicit expression. And you say, well, I want this to be an eigenfunction, so I want this to be a constant multiple of what I started with, which is this. So which constant multiple could it be? It has to be theta. So I want this to be theta times larger than this. This gives exactly the quadratic equation that Bass found by a more sophisticated method. This is elementary. Finally, I want to mention that we use an observation that we made together with Russ Lyons in a different context. So, and you can find this, for instance, as discussed in our book, which is there is another connection of the non-backtracking matrix to a real symmetric matrix. So start with, so of course the original adjacency matrix A, so this is the last slide. And it's a technical one, but still something that will be useful if anyone here uses the non-backtracking walk. So the original adjacency matrix A is symmetric, so we understand the relation very well. B is not symmetric, and it's related to A, but this relation has involves some work because B and A are on different spaces, a vertex space and an edge space. This matrix C is another matrix on the same space as B, namely on the edge space, but it's also real symmetric. So it's just this one. You take B, you invert it, so B is invertible, multiply by D minus 1 and add B. And this can be calculated explicitly. Here is the formula. And it turns out it's a symmetric matrix on the space of directed edges. Once you know that, you know it's directly diagonalizable. And now, again, every eigenvalue, there is a simple correspondence between eigenvalues of B and eigenvalue of C, right? If theta is an eigenvalue of B, then theta plus D minus 1 theta inverse will be an eigenvalue of C. So again, you get the same quadratic equation relating these eigenvalues. And this turns out to be, this matrix turns out to be very convenient in several considerations involving non-backtracking walk. Thanks for your attention.
Other questions?
Yes.
Exactly about this result, but more generally about Ramanujan graph. So, is there any importance to the precise number here that is 2 square root d minus 1? I mean, is there a real difference between Ramanujan and weakly Ramanujan graph symptomatically?
Well, I'm sure maybe Alex will have his answer to that, but I'll just tell you from my perspective. One thing we believe, but we haven't proved, is if you have, suppose you constrain a graph to be 2 root d minus 1 plus some delta, but fixed delta, not going to 0, then we believe, but we haven't finished the proof, that this does not force cutoff. So weakly Ramanujan, it's still about the number 2 root d minus 1 because it's about convergence to that number. But that number really is, we believe, very special. And it's because of, say, this Alon-Bopana, or precisely the Serre phenomenon that tells you there are a lot of eigenvalues there. So cutoff is due to participation of many forces in mixing. If mixing involves kind of doing one thing, crossing from one side of a barrier to another, there is no cutoff. But if mixing involves a lot of things that have to be arranged correctly, like all the cards have to fall in the right place, all the bits, then it tends to be cut off. Now, when you have Ramanujan, because you're constrained the largest eigenvalue to be in an area where there are a lot of other eigenvalues, there is no single eigenfunction that directs the mixing. And a single eigenfunction like that is, this signature of non-cutoff. When you have a lot of eigenfunctions that are all playing a role, then that is something that forces cutoff, although our theorems are not as ambitious as our intuition here. But that's the idea. And because, so once you go beyond 2 root d minus 1, there might be a single eigenfunction going there, and then there will be no cutoff. However, if you throw in transitivity, you can move that eigenfunction around. The eigenfunction should not have too many symmetries, so you'll get many eigenfunctions, and then I conjecture there's still cutoff in the transitive case, even outside Ramanujan. No. So that's one of the difficulties, that conjecturing cutoff without saying where it is leaves you, it's hard to prove. There's no reason it would be. No, but still, if you have high girth, and then maybe it will still be that constant. But anyway, so that's my partial answer from this perspective. Why 2 root d minus 1 is special? Of course, I mean, there's the Alon-Bopana bound, which tells you why it's special, or the spectrum of the tree. But for this problem,
it matters if you are on this side or this side of the boundary.
If you're tending to the boundary, then to first order it shouldn't matter. The second order terms will be affected, the window in the cutoff. Yes. Right. On the tree. Yes.
Is there an L1 object on the tree that you can attach to your constant to your boundary?
excited.
Sure.
Like two, you get exactly the spectral radius on L2 of the simple random walk, and of course the spectral radius in L1 of the simple random walk is 1.
Right. Well, yes. Well, since Anatoly Vershik is here, she mentioned the natural object is entropy on the tree. So take random walk on the tree. So this spreads out, but you can ask when is, but you know, as Russ mentioned in the lecture, we have random walk entropy, which and you can ask when is the random walk entropy equal to log n. And that will be the mixing time. When the entropy of the random walk on the tree reaches log n, that will be when the mixing time on the Ramanujan graph occurs in L1. So the L2 mixing corresponds to really a phenomenon of staying at the, staying too long near the starting point, while the L1 mixing corresponds to when is the entropy reaching the right value on the tree.
Thank you very much.
יובל, הרמות המקריות,
כן.
אז הם עדיין, אז הם יהיו עדיין,
ידוע שהם
סוטה הרבה מהשוק.
ידוע שהם מולטי רמנוג'ן, זה משפט של פרידמן וחברים, כן. אבל כנראה הם
מסתובבות מסביב לערך הזה גם מעורב.
אז יש ממש ההתנהגות של הספקטרום, יש חישובים של התוחלת, חישובים אמפיריים ויוריסטיים של התוחלת בסטיית התקן, ונראה